Right. So welcome back, students. After your inorganic reactions made easy, let us come back and start with this concept. Now, I said we need to study about the chemical properties of alkali metals as well as alkaline earth metals. That is where you'll be questioned, right? After completing the chemical properties of alkali metals, I also gave you the general information about the trends of alkaline earth metals, right? Now, after the trends, now let us come back to the chemical properties, very important, right? In chemical properties of alkaline earth metals, what are we going to learn? We are going to learn about hydrides, oxides, hydroxides, reaction with water, carbonates, sulfates, halides, nitrides, and complex compounds, right? Yes. So when I have to speak about hydrides, basically all the things, anywhere, any question may be asked to you. So let us see. So when I have to speak about hydrides, how is an hydride formed? So basically when I have to write the hydride form of this, yes, we very well know. Let me assume the alkaline earth metal as M. So M stands for metal. Let it be alkaline earth metals. It can be beryllium, magnesium, calcium, strontium, or barium, anything. Now, when it combines with hydrogen, right, it's going to form a hydride. Now, this is your hydride, metal hydride, right? Now, so when I have to speak about all the elements of the alkaline earth metals, suppose if I have start from first, magnesium hydride, MgH2. Right, so beryllium hydride also. So let us start with beryllium hydride because that is the first element. Let me explain about this. Beryllium hydride. Basically, this formation or this particular metal plus hydrogen, this particular thing, it's possible with magnesium, it's possible with calcium, strontium and barium, right? All these will combine. But when it comes to beryllium, formation of beryllium hydride, it will not directly react. Remember that. So what does it do? First of all, it's not going to form directly with this, and it's going to combine with a reducing agent like lithium aluminium hydride. So lithium aluminium hydride is a reducing agent, correct? Now what am I going to do? I'm going to take, let me take this as beryllium chloride. So what is the role of lithium aluminium hydride? It has to add hydrogen to beryllium, correct? So let's start. First of all, it's going to add, because I need to prepare BeH2. Normally remaining all will be prepared like this: magnesium plus hydrogen, calcium plus hydrogen, strontium plus hydrogen, barium plus hydrogen. But here in this case, lithium aluminium hydride, being a reducing agent, is going to add hydrogen and we're going to get BeH2. Done? Yes. After that, lithium chloride. After that, aluminium chloride. So all these three are formed. So remember this is the first, this is how beryllium hydride is formed. Now when I have to take the nature of these hydrides, right? The first hydride, magnesium hydride, this is ionic in nature. No, this is covalent, right? Yes, covalent, because the bond formed is covalent. Yes. When I have to speak about after this in magnesium, then next we have calcium, strontium and barium. Calcium hydride, strontium hydride and barium hydride, right? Right. So all these are ionic in nature. But what is the speciality? Most important thing you have to remember, you may be asked, what is the nature of calcium hydride? When I have to speak about calcium hydride is also called as hydrolith. What is this? It is called hydrolith. What does hydrolith means? Hydrolith means something which can act as a reducing agent. When I call something as a reducing agent, that means what is it releasing? It is releasing hydrogen. So calcium hydride is called hydrolith as it is acting as a reducing agent. That means it is releasing hydrogen. So that's why we call it as hydrolith. Remember this equation, right? So among the options, hydrolith, it's easy, right? So apart from this, when I have to speak about, or when I have to take magnesium hydride, let us see. Suppose when I have magnesium hydride, right. So now when I have to speak about magnesium hydride, as I said, let us see. If I take this magnesium hydride, and which suppose, let us assume we are combining it with water, dissolving it in water, hydride and water. So what is going to happen? It's going to just see here, it's very easy, nothing else. First important thing, when you dissolve something in water, it will break up into ions, isn't it? So first ion which is formed is Mg+2. Apart from this water molecule can be written as HOH. So this comes out as OH minus, right? And after that, what is left out? There's one hydrogen here, there's one hydrogen here. So what am I going to write? 2 hydrogen. correct? So now let us balance. So 2 2s are 4, correct? So to balance this, I need to balance this hydrogen also. Oh gosh. Then again this also. Now count 2 2s are 4 hydrogens here. 2 2s are 4, 5 6. 5 6, 2 to the 4 5 6. This is how it's going to balance. Now the same thing, suppose if I'm going to take calcium hydride, let me take hydrolith now. When I'm going to take calcium hydride, when I'm going to dissolve this in water, so what are the ions formed? It's going to break up into calcium plus 2 ion, plus it's going to break up into OH minus ion, plus the hydrogen gas whatever is there is going to be released out, correct? So now to balance 2 2 and 2. Now let us see here, water molecule, let me write this now normally. Now water molecule 2 2s are 4 plus 2 6. Here water molecules 2 2 2s are 4 plus 2 6. So this is how you're going to see. This is how the hydrides are going to, when you dissolve you get the respective ions, and calcium hydride is called hydrolith, and these are the basic things. Now let's come back and learn about oxides of alkaline earth metals. Right. Let's come back and learn about the oxides of alkaline earth metals. So when I have to speak about the oxides, normally because we very well know according to this one, the first element is beryllium, magnesium, calcium, strontium and barium, right? So when I have to speak about beryllium, beryllium is kinetically inert towards oxygen. Reacting with oxygen, it is kinetically inert, right? So we need to supply certain conditions, then only it's going to react, right? So it forms, it's inert, but supplying certain appropriate conditions, it forms. Why? Because an oxide layer forms on the surface of that. That's the reason it is chemically inert, right? So now when I have to speak about the oxides of this, now it's going to form two types of oxides. What are they? Metal plus oxygen giving me metal oxide, okay? 2. So this is one type. So which one will form this? The metal can be here, it can be, if I have to write, it can be beryllium, magnesium, calcium, right? So when I have to speak about the second type of metal oxide, it is again metal plus oxygen giving me MO2. Here strontium and barium, okay? Strontium and barium are going to form this type of oxides. Fine. So now what are the different types? If I have to speak about the nature of these oxides, nature, beryllium oxide, right? It is amphoteric in nature. Amphoteric means it's going to react with both acid and base, amphoteric. Fine. Next, magnesium oxide, calcium oxide, strontium oxide, barium oxide. Both the valency plus 2 and minus 2, they get cancelled, right? So remaining all, when I have to speak, they're basic in nature. They're basic oxides. Now when I have to speak about the amphoteric nature of beryllium oxide, as I said, how is this reaction? Basically, beryllium oxide, amphoteric means it reacts with both acid and a base. Now when it reacts with an acid, HCl, yes, so just see here, it's going to form, what is this? Beryllium chloride plus water, right? BeCl3 plus water. Fine. Now the same thing. If I have to react beryllium oxide with a base, so with the base I'm going to take aqueous solution of this. Then this together is forming a aqueous solution means, and let me take water. What does it form? It's going to form a complex, coordinate covalent complex. Who is that? If I take sodium as 2 moles, what is this? It's going to form a complex called Na2, close the square bracket, beryllium is here, and here OH taken 4 times, 2 and 2, so 4 times. This is your complex which is formed. What is the name of this complex? This is called sodium berylate. Sodium berylate. Sodium berylate is a complex which is formed. So this is the concept, or this is the this one about information about oxides. Now let's come back and meet with hydroxides. Right, let us come back and study about hydroxides. We have already studied about hydrides, oxides and hydroxides. Now, what are the type of hydroxides alkaline earth metals form? Basically, when I have to see, first one, it forms beryllium hydroxide, right? Right, valency of beryllium is +2, valency of hydroxide is -1. Next, after beryllium next is magnesium hydroxide, then calcium hydroxide, then strontium hydroxide, then barium hydroxide. Okay, these are the hydroxides. Now when I have to speak about basicity, basic nature about this, when I have to say careful. Now why am I speaking about basic nature? Because the presence of OH minus ion, correct? Now beryllium is less basic. The order of basic nature, basicity is beryllium is less basic than magnesium hydroxide, which is less basic than calcium hydroxide, which is less basic than strontium hydroxide, which is less basic than barium hydroxide. Yes. Now what is the reason? We'll see. Now what happened as we are moving down from top to bottom? First is your beryllium, magnesium, calcium, strontium and barium. Now what is happening in this case from top to bottom? Yes, what is increasing? Atomic size is increasing, or atomic radii or atomic size is increasing. When the atomic size is increasing, what will happen to the ionization enthalpy? Ionization enthalpy will become less. Less energy, I can pull out the electron. When ionization enthalpy is less, what will happen to the bond between metal and hydroxyl? The metal and hydroxyl bond will become weaker because the size is increasing. When the size, right. So next, when the metal and hydroxyl bond is weaker, I can easily break this bond. When I can easily break this bond, release of OH minus becomes easier. Yes. So now what is the concept? Metal bond is weaker. So what will happen? Release of OH minus is easier, isn't it? So release of OH minus is easier. When release of OH minus is easier, what will happen to basicity? Basicity obviously will be high. That means the size is larger, ionization enthalpy is lower, metal bond between barium and hydroxide group is weak. So easily it can donate the OH minus, hence it is a stronger base. Release of OH minus is easier, hence BaOH taken twice is a stronger base than BeOH taken twice. Yes, this is the concept. Fine. So next, when I have to speak about the nature of this beryllium hydroxide, when I have to speak, it is an amphoteric hydroxide. A amphoteric hydroxide. Remember that. So remaining all not a problem. It's easy. So remember as a special point, beryllium hydroxide is an amphoteric oxide. It reacts with both acid as well as base, which I've shown in the earlier this one, that is in oxides. Now let us come back and start. Do one question which is very important based on hydroxides. Right. Now let us do one question related to your solubility of hydroxides. So why are hydroxides less soluble in water as compared to alkali metal hydroxides? Okay, very nice. So basically when I have to speak about alkaline earth metals, so let us write the hydroxides first and support that question to this answer. The first hydroxide is beryllium hydroxide. Second hydroxide is magnesium hydroxide. Third is calcium hydroxide. Fourth, strontium hydroxide. And fifth, barium hydroxide. Now when I have to speak, beryllium hydroxide and magnesium hydroxide are incompletely, they're insoluble in water. So they are insoluble in water. Right. When I have to speak about this calcium hydroxide and this one, they are sparingly soluble in water. This calcium hydroxide is sparingly soluble in water. And when I have to speak about barium hydroxide, strontium, they are readily, immediately, as soon as you dissolve in water, they are readily soluble in water. Now they are asking you readily soluble in water. So with this condition, what can I conclude? I can conclude that down the group, when I move from top to bottom, in this group, what is happening? Solubility is increasing. Okay, when the solubility is increasing, what is a factor which you can immediately relate? That means when this is soluble, it can easily release OH minus ions. When it is releasing OH minus ion, what is increasing? Basicity is increasing. Very good. So from top to bottom, solubility is increasing means basicity is increasing. This is the concept. Yes. Now let us relate it with hydration enthalpy and lattice enthalpy. Whenever they ask you, try to speak in terms of hydration enthalpy. So what is hydration enthalpy? Hydration enthalpy is, suppose if I have to take hydration enthalpy is, if I have to speak in simple terms, it is a bond formed between the atom and water molecule. Or the energy released. The energy released when a bond is formed between an atom and water molecule, right? Now, so when I have to speak in terms of alkaline earth metals, the hydration enthalpy remains unaltered. It will not change from top to bottom. That is the first thing you have to remember. So hydration, okay, let me write it as delta H. That is delta hydration enthalpy. What is it? It's remaining unaltered because the bond formed between the atom and water molecule, right? So unaltered, it will not change. Now I'm going to speak in terms of lattice enthalpy. So when I have to speak about lattice enthalpy, now as I go down, fine, so what is happening? The ionic size is increasing, obviously, because number of shells are increasing. When the ionic size is increasing, the lattice enthalpy starts going down, it starts decreasing. So that is the important concept here. So what do we say? From top to bottom, as ionic size increases, what is increasing? Lattice enthalpy starts decreasing. Lattice enthalpy starts decreasing. Now we also have a formula, isn't it? What is this? What is that formula? Let's see. Delta H lattice enthalpy minus delta H hydration enthalpy. Hydration enthalpy is equal to delta H solution. Okay, this is what we have studied. So according to this concept, the alkaline earth metals have lesser solubility compared to alkali earth metals. So now let us come back and learn the reaction with water. One question was asked in one of the NEET paper, so I thought I'll cover this concept so that we can relate this concept when we do the MCQ. Now let's come back and see the reaction with water. So when I have to speak about the reaction with water, so one important concept, like it's not a concept, basically some more small information. When I have to speak about all the metals, beryllium, magnesium, calcium, strontium, barium, right? Now among this, beryllium is the only alkaline earth metal which will not react with water, both the room temperature as well as boiling water. So it's not going to react with water, both the conditions. Room temperature also it will not dissolve, boiling water also not dissolve. When it comes to magnesium, magnesium dissolves only in boiling water. Remember that. So when I have to speak about calcium, strontium and barium, all the three will immediately dissolve in water. Vigorously they are going to dissolve. So they will vigorously soluble, right? So now let me speak after giving the general information. Remember this, if they give you an option, don't try to put a product form, no reaction, right? So when I have to speak, what is the type of what is the reaction or general reaction which forms? Suppose when I take this metal, any of these metals, okay, except beryllium, solid. Now I'm going to dissolve this in water. So when I dissolve this in water, what will happen? Obviously it will break up into ions. This will become M+2 because it is a bivalent cation, isn't it? Group 2, isn't it? Right. Apart from that, in this water molecule you have H in OH. This OH comes out as OH minus. Apart from that, hydrogen is still there. Hydrogen is still there, which now let us balance. Now if I take, now OH is this one, isn't it? So let me take this as, instead of this, let me take 2. So this also will be 2. Now 2 2s are 4, 2 hydroxyl group and hydrogen gas. Simple, isn't it? Right. So now what should you remember? Suppose I said this is okay, soluble, boiling water. This is soluble or vigorously soluble in water. But how will you get beryllium? How will you combine when you have to dissolve? Only option is, if you want that particular beryllium to dissolve in water, beryllium carbide reacts with water. This reacts with water, beryllium carbide. Now what is the product formed with this beryllium carbide? When this reacts, first one, beryllium hydroxide. Now see here, we have prepared hydroxide like this only, and the leftover would be after beryllium hydroxide. The next one is methane. See here, this is very important for you. You need to remember this. Now let us balance. Here 2 2s are 4. Okay, so 4 plus 2, 6. Here let me write this as 3. If I write it as a 6, now oxygen, if it is balanced or not, let's see. Okay, fine. So beryllium is 2. Let us balance from beryllium and see. Okay, let me see. Beryllium is 2. So let me write 2. Now how many hydroxyl groups are there? 2 2s are 4. 4 plus 4, 8. Right, so how many oxygens are there? Right, 2 oxygens. 2 2s are 4. Okay, so here 4 hydrogens, here 8 hydrogens. So let me write this as 4. Now let's see. 4 2s are 8 hydrogens here. 2 2s are 4 plus 4, 8 hydrogens here. Beryllium is 2, beryllium is 2, oxygen is 4, oxygen 2 2s are 4. This is the balanced reaction. This is how you can prepare. But when I have to speak this for solubility, the solubility is very much less compared to alkali metals. So remember that concept. So this is the important information which you require for when you see the reaction with water. Let's come back and do So we'll speak about carbonates and their order also. let's go back and speak about carbonates. Now when I have to speak about carbonates, let us see the order. So first of all, carbonates, beryllium carbonate, right, is, if I have to speak in terms of solubility, right, so beryllium carbonate solubility is greater than calcium carbonate, magnesium, right, magnesium carbonate, which is greater than calcium carbonate, which is greater than strontium carbonate, which is greater than barium carbonate, right. So now what is the reason? So reason is, now when I have to speak about, whenever a solubility concept is given to you, or whenever a stability concept, or solubility rather, KSP, we speak in terms of KSP, isn't it? Let us take. Now when I have to speak about barium carbonate, now we are writing the reason why is it less. So why is the solubility less compared to beryllium? So this particular thing, when you dissolve it in water, it breaks up into Ba plus 2 plus CO3 minus 2. This is an aqueous state, this is also an aqueous state. Now when I have to calculate the KSP value of this, KSP is equal to the product by reactant, right, normal, right. So when I have to speak about the KSP value of this particular thing, it was found to be 5 into 10 raised to the power of minus 9. Which is very, very smaller value, isn't it? Yes, so 10 to the power of minus 9. So what is the important concept which you should remember? If KSP is higher, solubility will be more. Remember that. Solubility is more. This is the important thing. Which KSP higher means solubility more. Right. So let's come back and discuss about the sulfates now. We have discussed about hydrides, oxides, hydroxides, reaction with water, carbonates and sulfates. Now let us come back to sulfates now. I need to discuss about sulfates. So when I have to speak about sulfates, what are the type of sulfates alkaline earth metals form? First of all, the first sulfate is beryllium sulfate. Then after this, calcium sulfate. Okay, beryllium, magnesium sulfate. Then calcium sulfate. Then strontium sulfate, then barium sulfate. When I have to speak about the solubility of the sulfates, you may be asked a question based on solubility. Let's see this. Beryllium sulfate is more soluble than magnesium sulfate, which is more soluble than calcium sulfate, more soluble than strontium sulfate. Now when I have to speak about these two, they are almost, they're insoluble in nature. Why are they insoluble in water? Let us see the reason. Basically, whenever you are going to speak about solubility concept, remember, either you'll speak in terms of KSP, that is one. And the second important thing, you can speak in terms of two important concepts, that is hydration enthalpy as well as lattice enthalpy. Remember this, lattice enthalpy, right. Now what is this? Suppose if the hydration enthalpy is greater than lattice enthalpy, if the hydration enthalpy value, that is when the bond energy released when the bond is formed between the atom and the water molecule, if this is higher, then the salt is soluble in nature. Right. Now the same thing the other way around, if hydration enthalpy is lesser than lattice enthalpy value, this is lesser, hydration enthalpy when the bond, if the energy released is less when bond is formed between an atom and water, or water and atom, then that particular atom, metal atom, then if this is less, then the salt is insoluble. Now let us come back to this case. So when I have to speak about barium sulfate, in case of barium sulfate, the hydration enthalpy is lesser than lattice enthalpy. Right, so because of this reason, you can directly write that, because of this reason, why? Once again, in case of BaSO4, hydration enthalpy is less than lattice enthalpy. Right, the amount of energy associated when one mole of an ion is formed from its gaseous atom, that is lattice energy, isn't it? Lattice enthalpy, right. So hydration enthalpy is less than lattice enthalpy, hence barium sulfate is insoluble in water. So when I speak about this one, beryllium sulfate, this is the other way around. Hydration enthalpy is greater than lattice enthalpy in this case. In case of barium sulfate, hydration enthalpy is less than lattice enthalpy in this case. That's it. Right. Let's come back and speak about halides of alkaline earth metals. Now, when I speak about halides, let us see what is the type of halide it's going to form. Now, basically, your metal combines with halogen. Now, X can be fluorine, chlorine, bromine, nitrogen. Right. So, they're going to combine and form halides of type MX2. Now, let us see. Now, if I have the same thing, let me write M, metal combines with HX. Metal oxide combining with HX. Metal carbonate combining with HX, metal hydroxide also combining with HX. Everywhere, let me take 2 moles of this. Now what happens when it combines? The first thing, it's going to form an halide of type MX2 and the leftover hydrogen. Now in this case, MX2 of water. In this case, it's going to form again the same type of salt, MX2, and what I'll be left with? Water and carbon dioxide. Water and carbon dioxide. Now, in this particular case, again MX2 type, MX2 plus water. Okay, there's no carbon dioxide. So, to balance that water, I'll write 2. 2 2s are 4, 2 2s are 4. Right, these are the different types of this. Now, when I have to speak about beryllium halides, right, like let's come back and see beryllium halide, how is it dissociating? So it's going to form a complex of beryllium halide. Beryllium forms a coordinate covalent complex with ammonia. Let's see that. Right, and we speak about the nitrides of group 2, that is alkaline earth metals. They're going to form nitrides of type M3N2, right? The valency of nitrogen is 3 and the metal is divalent in nature, so +2. So when I have to speak about calcium and nitrogen, so let they both combine to form CaN. Now, right, nitrogen valency is 3, calcium valency is 2, so 3, so 3. So when I have to speak about magnesium, magnesium combines with nitrogen forming again MgN. Valency of nitrogen is 3, valency of magnesium is 2, because magnesium is 3 here, that is 3. So these are the types of nitrides formed, the ionic compounds which are shown by alkaline earth metals. Right. Now, let us come back and learn the structure of beryllium chloride. So, beryllium chloride shows 2 types of structures. What are they? One, let us write that. One would be, it's going to show a structure in vapor state, one structure in vapor state, other in solid state. Let us write. So, when does this show what type of structure, which temperature also you should remember? Vapor phase. Okay, let us write that as vapor phase is one type of structure. Second is in solid phase. Right. So, when I have to speak about vapor phase, here the temperature maintained is greater than 1200 Kelvin, then shows in vapor phase. Now, when it comes to solid phase, it is less than or below 1200 Kelvin, right? So, when it is in vapor phase, remember, this is going to show a monomer, only monomer. But when it comes to a solid phase, it exists as a dimer. Right. And next important thing, when I speak about monomer, the shape of the molecule is linear. Here, when I have to speak about solid phase, here dimer, the shape is, or if I have to speak, it is in the form of polymeric chains. I'll draw that chain, you will understand that. Fine. So, when I have to speak about this, it is zero dipole. There is no charge, zero dipole moment. Now, let us see the structure. It's a linear. So, beryllium chloride, isn't it? BeCl2. So, beryllium in the center, one chlorine here, one chlorine here. This is the structure in vapor phase. Now, when I have to speak about the solid phase structure, I said polymeric chains, isn't it? So, polymeric chains means how is this formed? Beryllium is here, right? One chlorine is attached here, one more chlorine is attached here. There is one more beryllium right here. Now this is bridged with one more chlorine, bridged with one more chlorine. Now again, this is again bridged here, this is bridged here, and this chlorine and this chlorine. This is how is the polymeric chain. Now let us write the bond angle. Here in this case, the bond angle is 98 degrees. Fine. Now the bond, this in between this beryllium and chlorine, this is 206 picometer, and from here till here it is 263 picometer. Fine. So this is what is the thing. Fine. Remember 202 picometer. So this with the structure. So remember when the exam they ask you solid state and vapor phase, you need to remember this data. This is the polymeric chain. Here when I have to speak, they are bonded with covalent bonds here. They're also bonded with coordinate bonds also here. So 2 chlorines with covalent bond, 2 chlorines with coordinate covalent bond. So both the 2 types of bonds are existing with beryllium and 4 chlorines around. With beryllium 1, 2, 3, 4. Here it is only linear structure in this way. This gets cancelled, this dipole gets cancelled. So the net moment mu is 0 in this case.